All right, geometry students, here we go with Chapter 10, Section 2. In 10.1, we did areas of parallelograms and triangles, and today we move on here and do areas of trapezoids and rhombuses and kites. So it sounds like a lot. I'm not sure we're going to finish all of this here in one section. We might do this in 2 videos. We will see how it goes. Okay, so the first thing we're going to start off with right here is the formula for area of a trapezoid. And that one is a little bit of a complex formula right here, but not too bad. A couple things to remember about a trapezoid as we look at it over here on the right-hand side. Trapezoid is a quadrilateral that has one and only one pair of parallel sides. And those two sides are called the bases. The other two sides of a trapezoid are called the legs. We don't really use those at all, though, in the area formula, so I'm not going to worry too much about that. We do have a height involved in a trapezoid as well. And just like we talked about in 10.1 with parallelograms and with triangles, it's really important to understand here that the height has to be measured perpendicular to not just one of the bases, but actually perpendicular to both of them, since those two are parallel to each other. So this formula here for area of a trapezoid is as such. It is 1/2 multiplied by the height of the trapezoid multiplied by the sum of the two bases. Okay, now the reason for all of that involves the idea that if we were to take this trapezoid, and I'm going to do this kind of a low-class way and kind of clone this thing looking like that, we actually end up then with two trapezoids. Here's number 1 and here's number 2 that are identical to each other. And if we put them together, it actually makes a parallelogram. And the base of that parallelogram, this base 1 up here is the same as this base 1, so the base of that parallelogram is the sum of base 1 and base 2 put together, and the height of it is just h. So the area of the entire parallelogram is h multiplied by the sum of base 1 plus base 2. Well, we don't want the entire parallelogram. What we're interested in right now is the trapezoid, which is making up exactly half of that parallelogram right there. So if we wanted the area of just half of this figure right here, we would just cram a 1/2 in front of it, and that would get us the formula right here then for area of a trapezoid. So dear God, I made a mess out of that diagram. So I'm going to undo most of this right here, and let's get down to simple tactics right here. Okay, so area of a trapezoid is 1/2 times height times base 1 plus base 2. So let's take a look at our first example right here. Guys, I got a little sloppy in some of my diagrams right here, and I probably didn't label things as well as I should have here in terms of things being parallel, but hopefully we can make that assumption right here. So, as we always do in this chapter and the next chapter, we're going to start off with a formula here that area of a trapezoid is going to equal 1/2 multiplied by the height of that trapezoid times the sum of base 1 plus base 2. And not to insult anybody, but let's remember order of operations here, everybody, that what happens inside the parentheses has to be done first. So step 2, fill in what you know. Area of this trapezoid is 1/2. The height is going to be this 6-inch altitude right there in red. So I'll put that in a set of parentheses, although that's not necessary. But the second set of parentheses is important. The sum of the two bases, those are the two parallel sides, which very often, although not always, are going to be found on the top and the bottom of your trapezoid. So a 10 is the length of one of our bases, and 13 is the length of the other. And step 3, just go ahead and simplify or solve or whatever you need to do right here. The 1/2 multiplied by that 6 is going to get us a 3. The 10 plus 13, should have actually talked about that first, is a 23. So this 3 here gets multiplied by this 23 to make 69, and we were in inches right here, so that's going to be 69 square inches for the area of that trapezoid. Once you get the formula down, this stuff isn't really all that bad. Okay, let's take a look at example B here, which puts a spin on this in a way that a lot of our problems in the book here this year do. In this problem, they have given you the area of the trapezoid, and they're asking you to come up with the value of n. Now, as we look at this figure, this is a trapezoid that a lot of us are going to think has been flipped on its side. Try to identify the two parallel sides. And again, arrows really would have been better to include right here, but it's the left and the right that are the two parallel sides. That means that the 50 and the n are the two bases. All right, that's important. So here we go. Step 1, write down your formula. Area of a trapezoid is 1/2 times its height times, in parentheses, the sum of its two bases. And what we can see here, guys, is that there is actually 1, 2, 3, and 4 variable quantities within this formula. We better know the value of 3 of them in order to be able to figure out the 4th. And here we go. Fill in what you know in step 2. They're telling you that the area here is 1,200 square centimeters. So this is different from most problems where we actually know the area. Okay, from there, everybody, what do we have next? We're going to go with a 1/2 right here. The height of that trapezoid that's the interesting part in this problem. And if these are the two bases here of the 50 and the n, the height is the perpendicular distance between them. Well, here's our right angle right up there. That means that this red auxiliary line right there is going to be our height. And that's what we're going to need to figure out, because the rest of this problem isn't really all that tough. So, in taking a look at what's going on right here, we see that we have a right triangle right over there with a leg of 10 and a hypotenuse of 26. All right, so let's try to do this the way that we were back in the day. Let me draw this just a lot bigger over here to the side. We had a 26 side over here, and we had a 10 right over here on the leg on the left, and then we were looking for h right down here on the bottom. When you know two sides of a right triangle, you certainly could do the Pythagorean theorem, but what fun would that be? We're going to try to mess around with Pythagorean triples instead. Greatest common factor of 10 and 26 is nothing more than a 2. That's not very exciting, but let's divide that out and see what happens. The 10 divided by 2 is going to get us a 5 right here. The 26 divided by 2 is going to get us a 13. So when we think about our Pythagorean triples, one of the ones that we wrote down, the second one in fact, was a 5, 12, 13 Pythagorean triple. Sure enough, this one has a leg of 5 and a hypotenuse of 13. So the other leg here gets a 12 inside the figure. But now, to figure out the length of h, we're going to multiply this 2 times that 12 right there and get that h, our missing side, has a length of 24. Okay, so back to the original diagram right here. We now know that our height is 24, and that's what's going to go right here in the place of h. Okay, and then filling in everything else we know, in parentheses, the sum of our two bases. The bases we said were the parallel sides. One of them has a length of n, and the other one has a length of 50. And that is what we needed, everybody. There were 1, 2, and 3 of the 4 variable quantities that we were able to put values in for, and we did okay with that. As far as where to go next in order to solve this, again, I think I might disagree with some of you guys in terms of the best way to do this, but here's how I would probably go about it. The 1/2 times the 24, I think, should probably be simplified first. And half of 24 is a 12, and we multiply that by n plus 50. Now, every single one of you is going to look at this here and tell me that we ought to distribute the 12, but all you're doing is you're heaping an extra layer of crap on top of your variable n that we're just going to have to divide out in the end anyway. Remember, the goal right here is to get n by itself. We want to take things away from n, not put more things on top of it. So instead of distributing, we're going to divide both sides by 12. And let's see where that gets us right here. Okay, so the 1,200 divided by 12 is just going to be a nice even 100. And on the right side, the 12s cancel, and that leaves us with an n plus 50. Now we're going to subtract a 50 from both sides. And here we go, guys. N is equal to, and we ended up with a 50 over here as well. All right, and that was our answer for example B. Okay, let's take a look at where we're going next here. Oh, did that already? All right, let's move on to our second formula here in section 10.2. And this is the formula here for area of a rhombus. And a rhombus, if we recall, is a parallelogram that has 4 congruent sides. So each of these 4 sides within the original rhombus are congruent to each other. And we end up with this formula here, guys, that the area of a rhombus is 1/2 times d1 times d2. Remember, everybody, that this is multiplication when there's no other sign listed. And the important thing to understand here is that the d in this formula stands for the diagonals. AC, the distance from one point to its opposite vertex, is the length of one of your diagonals. And then BD, from one other corner to the opposite one is the length of your other diagonal. So we should remember it this way, that the formula for the area of a rhombus is 1/2 times diagonal 1 times diagonal 2. All right, let's see this one in action right here. So, again, not a very good diagram on my part, so I probably should have put tick marks here to indicate clearly, so there was no assumption, that all four sides here were congruent and that this figure was a rhombus. So let's start with our formula here. Area of a rhombus, then, is going to equal 1/2 times diagonal 1 multiplied by diagonal 2. Step 2, fill in what you know. We do not know the area. That's what we're looking for. There's a 1/2 right here. One of the diagonals, this one from top left to bottom right, was given to us, and that one right there was going to be 12 centimeters. The other diagonal, we don't know. In fact, the weird thing about the other diagonal is it wasn't even drawn for us. The other diagonal is going to go from this vertex in the lower left corner to this vertex up here in the upper right. So I'm going to go ahead and draw that diagonal there in red, and that red segment is what we now need to figure out the measure of. Well, to do that, we've got to remember a couple of important things about diagonals within parallelograms and rhombuses. The first important thing to note right there is that in any parallelogram, the diagonals bisect each other. This point here in the middle is the midpoint of both this diagonal and the red diagonal. Now that blue one that was drawn there had a length of 12. That means it gets bisected into a length of 6 and 6. Now that's true in any parallelogram. However, since this thing is also a rhombus, an important property of the diagonals of a rhombus is that they are perpendicular to each other as well. And that becomes really interesting here now, because when you draw those two diagonals right here, you now form four congruent right triangles using one side of the rhombus and then half of a diagonal in each case. So what we have right here, everybody, is a right triangle with a leg of 6 and a hypotenuse of 10. Again, we could use the Pythagorean theorem, but again, you could divide out a 2 right there and find that there's this one's actually going to be a Pythagorean triple. Remember, everybody, that the most common and simplest Pythagorean triple out there is 3, 4, 5, and a multiple of that triple, if you doubled every side, is 6, 8, 10, and that's exactly what we're dealing with right here. So this red piece that goes from here to here is going to have a length of 8, and there's your 6, 8, 10 for that Pythagorean triple multiple right there. Now, it's really tempting then to say that the other diagonal has a length of 8, but that's not correct. The 8 was this piece right here, which means that this red piece down here is an 8 as well, and when we add those two together, we're going to get 16 now for the measure of that second diagonal. And that is everything we needed here, everybody. So what do we got here? Oh, a couple ways to do this, but I'd probably just go in order. A 1/2 times 12 is going to be a 6, and a 6 times 16 is going to be 96. Everything was measured in centimeters here, including the 12 centimeters and the 16 centimeters for the diagonals, so the area is going to be 96 square centimeters. Okay, we're going to stop this video right here. We'll come back and we'll do part 2 in a moment.